And we're keeping on the theme of how AI can help you make your testing significantly more efficient. I, for one, want to learn how to do that. So without further ado, please welcome Sonya.
Good afternoon, everyone. It's a pleasure to be here at Programmable 2025 in Melbourne. Today, I want to dive into a topic that has got everyone buzzing recently: how generative AI is transforming automated testing. We are not just talking about incremental improvement. We are looking at a fundamental shift in how we approach automated testing. In this session, we will cover techniques for improving AI's understanding of context, how to customize the model specifically for generating test coverage scripts, and design AWS architecture to scale the solution. Before talking about how generative AI can transform automated testing, let's take a step back and look at the challenges we face with the traditional automation. As we all know, in today's digital landscape, automated testing isn't just a luxury. It's a backbone of reliable software delivery. Companies with a strong test automation see 70% faster release cycles. But here's the thing. Traditional automation testing isn't perfect. Apps tests break easily when apps change. This leads to substantial manual effort in creating new tests, fixing broken ones, maintaining existing ones, and repeating. It feels like running an endless treadmill. Let me share a story that probably sounds familiar to many developers. Just last year, I worked on a project to send all backend API to a different service. I made what seems like a tiny change for account number validation. As a result, half of 600 test cases lit up like a Christmas tree with failure. And what could be even worse is dealing with the flaky tests. This hit close to home for every developer. How many times have you clicked the review button in the hope that next round of testing will pass? And let's not even talk about legacy system with no automated testing. Our team worked on a project last year where we spent weeks just for setting up a testing framework and pipelines. Even after that, writing tests for each scenario felt like piecing together a puzzle while some pieces were missing. It was time-consuming, and the progress felt painfully slow. These are not just inconveniences. They are actually holding back our ability to deliver quality software at speed. So here we are, facing this perfect storm of challenges. And they bring us to a question that keeps me up at night. How can we fundamentally change the approach to testing? Think about it. What if the test can adapt to changes automatically? What if there are no flaky tests in test suite? What if we can create a comprehensive test suite in minutes rather than weeks? It sounds too good to be true, right? But that's where generative AI steps in. And it's not just hype, it's already happening. Generative AI leverages machine learning to spot patterns from large amount of training data and create a new content. It's kind of like how you learn by reading thousands of books, but way much faster. One of the most powerful features is the adaptability. Instead of wasting hours fixing broken tests, AI automatically adjusts the changes to match the update. And the flaky test, no problem. AI can figure out the root cause by analyzing historical test results, whether it's timing, dependencies, or other issues. AI can fix them too. But the magic doesn't stop there. Imagine this is like a super-powered alien friend who understands the natural language, translate requirements into test scenario, and even generated test cases and synthetic data. Since it's amazing at analyzing patterns, it's also good at catching at those sneaky edge cases we possibly miss. As a developer who loves coding but not babysitting tests, I found this technology keep me in the flow, let me focus on building great features. Before we delve into AI-powered testing, let's demystify some key terms that might sound complex, but are actually quite intuitive. Let's start with a simple definition. You may often say large language model or LLM in headlines. But what are they? They are AI systems trained on massive amount of text to understand and generate human text. You may have heard some of them, like OpenAI's GPT, Anthropic Claude, open source one like DeepSeek or Cogent, which excel in code generation. But to make a large language model more useful for specific tasks, we may need to refine its ability. That's where fine-tuning comes in, a process where we take a model that already understands general pattern and train it further with the specific data to make it highly skilled in one task. After understanding these foundational concepts, let's talk about how can we make a model even smarter. Imagine teaching AI to get the most relevant information from a big pile of data. This process is usually called retrieval augmented generation, also known as RAG. First, the retrieval. Think of this as searching through a digital library for relevant information. Then comes augmented. This is where the system combines the retrieved information with the existing knowledge. While generation is in the name, it's actually the final step, not the part of the RAG system itself. It's the last step where AI produces the responses based on the retrieved information and the AI capabilities. But how exactly does this mechanism work behind the scenes? Let's go a bit deeper. The RAG system uses embedding and vector search techniques to retrieve the relevant information from a database. This retrieved data is processed into a structured prompt that tells the model the context, background, and the information it will need to learn in order to answer the question consistently and reliably. It's like giving AI a cheat sheet for better results. Now let me show you a quick proof of concept. How we can integrate with a RAG system, fine-tune with a large language model with 100 data size to generate test coverage scripts for a simple registration form. The form in this example contains first name, last name, email address, organization or agency, and a register button. I wrote a program to extract a few names and IDs from the form, which will fed into the RAG system. Let's start with the retrieval stage. In this example, I set up a local Milworth vector database and prepared the data, including the field name as a key and a document with the relevant information. For example, I use organization for the field name, organization or agency in the data file as a key, and as a document, this field must be no more than 100 characters. Then the program loads this data file into the database. During the loading process, I converted the field name into vectors and stored them in the database along with the documents as metadata. Then I query the database using an AN search based on the vectors of the field name extracted from the form to retrieve the document for each field. Then I got all the contextual data I needed. And now that comes to the second stage, the augmented process. In this stage, it combines the information I retrieved previously with the form ID passed earlier from the form. Eventually, it constructs a prompt with all the field IDs, names, and additional contextual information for each field. So this process is very flexible. It pulls together all the right content to create a solid prompt and help the model to generate reliable results. I quite like how vector search works. It's like a smart matchmaker that understands the meaning, not exact words. Even if your labels are a bit different, like this example, I use organization or agency in the data file in the form, while just organization in the database. It can still connect the dots. It's kind of like you may call your friend William, while someone else call him Will, but you both know you're talking about the same person. So the vector search is clever enough to understand these connections. Then you don't need to worry about having a perfectly matching few names. Before the model takes the prompt and produce the result, I first fine-tune it with 100 data sets to improve its ability to generate test coverage scripts for testing registration form. In this example, I use a CodeGen 350M model because it's lightweight, open source, specialized in code generation, and feasible to fine-tune with a red local setup. And it's perfect for proof of concept. The secret sauce is really in how I build the training data. I spent lots of time creating two solid pieces. First, I wrote a detailed description for form elements, input and buttons, along with notes about how they should behave in different situations. Then I paired this with the actual test coverage scripts that showed both the standard testing scenario and those edge cases you would want to catch in a registration form. By giving the model two pieces, the what to look for and the how to test it, these data sets guided the model to generate reliable scripts. For model training itself, you use 80% of subset for training and 20% for testing, with a gradual learning rate to avoid overshooting optimal model configuration. It goes through the entire data set 3 times to learn patterns. I saved the checkpoint at the end of each epoch to document how data sets and hyperparameter tweaking impact our output. This process took several iterations. Okay, so here's the exciting part. The generation stage you have been waiting for. Let me share what I found during the test run. The model managed to write test coverage scripts for populating all input fields and submitting the form. It's not too bad because we only fine-tune with 100 data sets. But I did spot some gaps too. For example, there are minor syntax errors, no validation or error message handling. To address these gaps, we need to fine-tune a larger model, one with more parameters that can capture more complex patterns. Of course, this comes with its own challenges. These models are simply too large to run on local machines, unless you have a serious computing power and enough storage. That's why we need to leverage cloud-scale infrastructure to handle the workload efficiently. But it's not about having any cloud solution. We need infrastructure specifically designed for machine learning workload to give us the scalability and the efficiency we need. Here's a high-level AWS architecture that powers this solution. Let me walk you through how each component works together to support model training, deploying, and the running process. In this setup, we use Jupyter Notebook to design training jobs and configure all parameters. These jobs are processed smoothly in AWS SageMaker, which handles all the heavy liftings. SageMaker is an all-in-one machine learning platform that allows teams to build, train, and deploy without managing complex infrastructure. It's like having a fully staffed machine learning operation team at your fingertips. Behind the scenes, SageMaker automatically launches powerful compute instances when needed, retrieve the initial model and data set from an S3 bucket, and save the trained model to another S3 bucket. Once the model has been fine-tuned to our satisfaction, the deploying process is very straightforward. We can just deploy it to a SageMaker endpoint directly from the Jupyter Notebook. If you shift your focus to the right side for the running process, when a user is submitting a query, a lambda is used to process each request by first retrieve any contextual information, then it builds a prompt for the model, call the SageMaker endpoint we set up previously, run the model, and return the result. With this setup, what looks complicated on paper becomes a practical solution that can help us to solve the everyday problem. Now let me bring everything together with a vision that should excite every one of us in this room. We started by talking about the challenges with traditional test automation and the breakthrough we have been waiting for. Generative AI isn't just another tool in our testing toolkits. It's a paradigm shift that transforms those challenges into opportunities and moves maintenance to magic. With a RAG-powered model, we are not just ranking tests. We are building intelligent testing systems that understand the context, adapt to changes, and they even anticipate the edge cases. Minor code update no longer crumble tests. They now evolve naturally with your application. Through cloud-scale infrastructure for the whole process, test generation is even faster and easier. And what would have taken us days to do can now be handled by AI automatically in a matter of minutes. Here's the thing. We're not just talking about better automation here. This is about generative AI changing the game for how we build the software. We are standing at the start of something huge, while AI basically gives us developers superpower. And it's starting by solving those automation headaches that have been driving us crazy for years. The AI revolution in development is here, and the automation is just beginning. Thank you.